So let's take a look at what we know so far about magnetostatics and compare it to what we compare it to our development of electrostatics. Okay, so in electrostatics we found a surface charge densities. In magnetostatics we found surface bound current densities. In electrostatics we found volume charge densities, and in magnetostatics we have volume bound current densities. In our development of electrostatics, we identified a new vector, d, which was the sum of epsilon naught E plus P, and we rewrote Gauss's law in terms of d, where the source for Gauss's law was now just the free charge component. And we have no analogous equations over here in magnetostatics. So we're going to develop those analogous equations now. But before we do that, I'll just remind you of our development of d in electrostatics. So the procedure was that we rewrote, or we separated out the various charge contributions to our divergence equation in E. Okay, so this was the first step. So rho is always the total charge, and as far as the divergence of E is concerned, it doesn't matter whether the charge is bound charge or free charge. Charge is charge. We make a distinction here because it's useful to us to make a distinction. Bound charge comes from the divergence or the negative divergence of the polarization. Free charge is extra charge that we would inject into the material. But as far as Maxwell's equations are concerned, it doesn't matter where the charge comes from. But we separate it out in this way, and then we rewrite the bound charge as the negative divergence of P. Okay, so if we were now to substitute this equation into here, we could rewrite our divergence equation in the following way. Okay, so this was our development for the vector d, and of course d is this term here, that is d, and d is a useful vector for us to work with, and we're going to follow a very similar procedure in magnetostatics. So here we started in electrostatics with the Maxwell equation where the charges entered as a source. And we're going to do the same thing in magnetostatics, but of course it's now the curl equation. Right, so once again, we're going to separate out the total current density J in terms of a bound current density JB and a free current density JF. And once again, Maxwell's equation for the curl doesn't make any distinction in terms of where the currents come from, but it's useful for us to distinguish. This one, these are currents that we would inject into the material. These are currents that are present because there is a volume bound current density. And we're going to rewrite this term here in terms of the magnetization. Okay, so there is our analogous development in magnetostatics. This vector H here is B on mu naught minus M. It responds only to the free current, and this is analogous to our vector in electrostatics D that responded only to the free charge. Alright, so let's just make that analogy quite clear. Okay, so we have to be a little bit careful here. It's very tempting to think of the vector D being completely analogous to an electric field because this equation looks very, very similar to our divergence for E equation, and it's very tempting to think of H being completely analogous to a magnetic field B, but that really isn't the case. And the reason is the following. In electrostatics, the curl of the electric field is always zero in electrostatics. However, the curl of D is not zero. Not always. The curl of D is the curl of the polarization. Similarly, in magnetostatics, the divergence of B is always zero, but the divergence of H is going to be the divergence of minus the divergence of the magnetization. Okay, so how to interpret D and H then, given these results? Well, the way to interpret D and H is through their definition. So D is defined according to this equation. H is defined according to this equation. These equations are useful when we come to calculate, and that's about the end of it. It's important to, I think, to understand that the more fundamental of the fields are E and B, and the reason is that when we think about forces on charges, it's the electric field that matters for electric forces, and for forces on charges, it is the magnetic field that matters. So these are a useful calculational tool, but we need to be a little bit aware that they are different from the magnetic fields in the case of H and the electric field in the case of D.